Okay, hello everyone. So sorry that we had to do this special Zoom lecture because of a health issue I had. So this will be a special lecture, and I hope to cover something different. And as I said, as we did last on Monday, right? Last Monday, this month of this week, we actually covered the extreme order statistics. And so we will continue doing that and go into sample quantiles on next Monday as planned. For today, I think I want to cover something not in my lecture notes, which I didn't cover previously, but I think it's something important to know, which is the asymptotics of the maximum likelihood estimator, MLE, because we use MLE so often in our applications. So knowing why it is a good estimator would be very useful. So I posted a link to a lecture notes from an MIT open course to our CCLE under week 6. So if you go there, you should be able to find that typed notes over there. And I also post the link to the recording later. So I'm just going to go over the essence of what's about the asymptotics of MLE. So for those of you who are here attending this Zoom lecture live, so I would appreciate it if some of you can turn on your video so I can see those of you. And just to make sure that of your privacy. So basically, I think as long as you're muted, then your video will not be recorded in the recording, and only I will show up. But if you ask a question and you don't mind, then we can see you. Okay, so thank you for those of you who just appeared. And so for today, we're going to cover this asymptotics of MLE. So this is the way I used to teach during the past year when we did the Zoom lecture. So I hope you guys can see it well. If not, just let me know. Asymptotics of the MLE, maximum likelihood estimator. So to me, this is a very important topic and it has great relevance to our applications. So to answer this question, we will look at MLE in two aspects. The first is its consistency. And the question we want to ask is, let's say that we have an MLE denoted by this theta n hat, right? Hat means it's an estimator, and n means our sample size. And we are interested in comparing this estimator with our true parameter, the thing we want to estimate. And we denote that by theta. Okay, so recall that when we do MLE, we are usually in most cases, just starting from the simple things, we are under a parametric model, right? So a parametric model can be specified as parameter theta. So in this case, what we usually do is that we will assume our sample x1 to xn with sample size n can be considered as IID from some distribution whose density function can be specified by this f. Okay, so we will just write it as, let me just think about it. Maybe I'll just write it as f theta. Okay, theta is the true parameter that specifies the distribution. And this f is the PDF, probability density function. So that's how we write it. And recall that how we find the MLE. So to do that, we need to first write down the likelihood function based on the density. So just as a recap, the likelihood function is a function of a parameter. So its domain is a subspace of the parameter space. So it's not like the CDF. Right here, this function is defined as a function of the value of my random variable. So basically, the domain of this f is actually defined as the values that this xi, the random variable, can pick. So they are different functions. And the likelihood function, we often use this uppercase L. And here I would use the sample size as a subscript to denote it. So we call that likelihood of a parameter value m, theta. So maybe to distinguish the case between a true parameter, okay, I'll just put a 0 here. So, or we say theta 0 or theta naught. So that means the true parameter value from which our data is generated. While this theta can be any possible value of theta. And for any value, we could evaluate the likelihood function. So you can see that the prospective likelihood is that we fix our data, but we change the parameter value. And to assess how likely is my data coming from this particular parameter value. So in this case, the likelihood function is defined as the joint distribution, joint density. Okay, I just write it. The joint PDF of my sample x1 to xn given this parameter theta. Okay, and because we have IID of x1 to xn, we can just factorize this joint PDF as the product of individual PDFs. So I can write as f. So please note that here I'm going to use theta because this is the theta for which I'm considering as the parameter. And I don't know what's the true parameter. So I'm considering any theta of xi. So I have that. Okay, this is likelihood. But we know that this product is not as easy to work with as a sum. So this motivated us to, and also a lot of those PDF functions, this f, theta, involve exponential functions such as Gaussian, right? So in this case, a very common technique we use in statistics is to perform the log transformation. Then we obtain the log likelihood by taking the log of this likelihood, right? So we denote that we call this lowercase ln theta, which is defined as log ln theta. And then suddenly I can write it as the summation I from 1 to n log f theta xi. Okay, that's my log likelihood. And still you see the x1 to xn's are still IID. I still have that nice property. Now, given our past lectures, we have seen so many cases where the statistic is some average, is an average of IIDs. So if you look at it in terms of the x1 to xn for this formula, you can see that it is also a sum of IIDs, right? So basically, based on our knowledge, we already know that by the strong law of large numbers, we would have, if I divide this log likelihood by n, 1 over n ln theta, this will convert to what? I'm just writing, it could be almost surely, or it could be improbability. So both will work to what? To the expectation of one term, to the expectation of log f theta xi, right? I will have that. But one thing I need to be very clear is what this expectation is taken for. It's based on the true distribution of xi. That's where I take expectation. And its true distribution is based on the true parameter value theta 0. So I need to put it theta 0, okay? And then you see, if I expand this, it's basically the definition of expectation based on integration. So it's that I have log f theta x, okay? This is the thing I want to take integration for, times the density, which is f theta 0 x, okay, dx. This is it. So you see that in this expectation, I no longer have xi because it's the thing I'm taking expectation of. Xi will be gone, and what's left would be true parameter theta 0 and the parameter value I'm evaluating at, theta. So theta and theta 0 will stay in this expectation. Okay, so this is the first thing we should be clear, right? This is the log likelihood. Then what's the definition of MLE? The definition of MLE, okay, so maybe I should make it clear that this is a function I would define, just we will use this later. Let me give this a notation. How about I just call this function G, okay? I call this function G that involves theta and theta 0. So I will put theta 0 as given because theta 0 doesn't change, while theta would change. Okay, so what is MLE? The MLE, theta and hat, is defined as the maximum, the maximizer, argmax of this ln theta, of this log likelihood, okay, over possible values of this theta. So this is the thing we know. But something we don't know is something we're going to show you now, or may not be so clear about, not by definition, is the true parameter. The true parameter theta 0 is also a maximizer. And what does it maximize? So I'll tell you that it actually maximizes this G function. Okay, so maybe I can say it's the argmax of this, right? So then by just very simple one step, it's also the maximizer of this log likelihood divided by n, right? Divided by n doesn't change the maximizer. And for the true parameter, we're going to show you that this is actually the maximizer of this G function. In other words, if I have theta to be as theta 0, I can maximize this expectation. Okay, so how can we show that? So the thing to show that is I can show you this interesting fact. So think about this expectation, okay? So to prove this result, think about this expectation, and I'm going to show that the expectation of theta 0 log f theta xi, random variable, divided by f theta 0 xi. Okay, by definition, I just have, because log ratio can be written as the difference of two logs. This is just g theta 0 minus g theta 0 theta 0. Okay, I want to show that this is non-positive. Okay, this is what I want to show. And how do I do it? So this is something we use a lot in statistics regarding a function inside expectation. So we need to look at the shape of this function. And when we know this function log, if it's a linear function, then we can exchange the function with expectation. But log is not linear. Instead, we know it's a concave function. Okay, and for the concave function, we can apply Jensen's inequality. So this is how it looks. Let's see, log x. Okay, so it has this shape, right? And we can know that. So by concave, what it implies is that, so I don't remember this myself. What I usually does is I just draw this figure and see the relationship. So let's say you have two, just imagine in the simplest case, xi takes two values with equal probability 0.5. Okay, then the expectation of x would be here in the middle. Okay, and the log expectation will be somewhere here on the curve, while the expectation of two log values will be in the straight line, which is below the curve. So in this case, I would know that log expectation, okay, in this case, log expectation would be greater or equal than the expectation of log. Okay, so with this relationship, right here, I'm having expectation of log. What I can say using this result is that this line, expectation of this log xi f theta 0 xi by Jensen's inequality would be less or equal than the log of the expectation of f theta xi over f theta 0 xi. Okay, now we have something nice to work with. So for this expectation, we can expand it, as the definition. F theta x, f theta 0x times f theta 0x, right? The reason is because our expectation is taken under the true distribution with parameter theta 0, dx. So I have cancellation. But still, even though this f theta x is not a true density, but still under this value theta, this density is still a valid PDF. So when I do the integration over x, I will have a value of 1 for this integral. The log of 1 gives me 0. So you see, immediately I prove that this expectation of this log density ratio, actually, I should say it's either density ratio or likelihood ratio, both will work, would actually be negative, non-positive. Therefore, it immediately shows that theta 0, the true parameter, maximizes this G function. Okay, so then the question becomes, coming back to the left-hand side, we have, let me just put it this way. So we have theta hat m, the MLE is the maximizer of this average, okay? 1 over n. I'm just writing out the original formula. Okay, that's my MLE. While this theta 0, the true parameter, is maximizing the expectation of that, okay? Expectation of this term. So I will just write expectation under the true parameter value of log f theta xi. Okay, so what I have is that we have the strong consistency this thing converges, I'll just use the probability version, in probability to the expectation. This is what we have. But the question we don't know is, does the maximizer of the left-hand side also converge in probability to the maximizer of the right-hand side? Okay, that's what we need to solve this consistency question of MLE. So for this part, we don't have any issue, right? And also I want to say that this part holds for any fixed theta. So by fixing theta, you see the random variables, what we have is x1 to xn. So this is a strong law of large number result. But to obtain the maximizer conversion in probability to this, we need to vary theta, right? Theta is no longer fixed. So that's why for this one, we need a stronger result, stronger than this one. That means a stronger result. That means we have this convergence in probability, even though we vary theta, not just for fixed theta. What is that? Okay, so we actually have a name for this result. It's called uniform strong law of large numbers. Okay, what does that mean? By uniform, it's just like uniformly continuous. We are trying to talk about all possible values of this theta, not just a particular theta. So what we say here is that, so compared to what we have this, right? This is like point-wise strong law of large number, point-wise in terms of theta. So to make this stronger, what I want to have is if I take the sup over theta for the difference between this average and the expectation. So if I do this, I take the difference, I take the absolute value. I want the sup to go down to 0 in probability. That's what I want. Okay, so if we have this result for this function, then we would have, that will give us a way to prove that the maximizer of this would converge in probability to the maximizer of this. So that's the whole logic for deriving the strong consistency of the MLE. So first question is, when does this uniform strong law of large numbers hold? So we need some technical conditions to ensure this, but mostly I can say that we need a continuous. We need this function to be continuous. So what we need? The first one is this log f theta. Let me see this. Okay, this is a function. I need it. Maybe I just put it here. This, okay, theta and x. I need it to be continuous in theta. Okay, actually theta is down here for all x. So given an x, if I fix x and vary theta, I need this to be continuous in theta. That's the first thing. And the second thing is that I need to find an upper bound with finite expectation of upper bound function of this f theta x, a function of x, so that that function has finite expectation. Secondly, I need a function and k such that I have this absolute value of log f theta x is less or equal than kx. Okay, this k has nothing to do with theta. And the expectation of k at this random variable, let me just say xi, this expectation must be finite. So here expectation is again under the true distribution. So with these two conditions, and also sometimes we need to talk about that the space of this theta to make it nice. So basically we need this theta 0 to be an internal point of the domain where this theta can belong to. So with those technical conditions, we can go from what we have, the point-wise convergent, point-wise strong law of large numbers to this uniform strong law of large numbers. And with this, we can actually show that if the density function PDF of the sample we assume to come from satisfies the conditions for uniform strong law of large numbers, with this, then we can show that the maximizer of this will converge to the maximizer of that. Okay, so with the uniform SLLN, we can show that the maximizer theta n hat would converge to, in probability, to the maximizer of the limit theta 0. Okay, so for this step, how do we go from uniform strong law of large numbers to the convergence of the MLE. So I'm not going to go into detail for that. But for those of you who are interested, I think I'm going to take pictures about this topic from the textbook I recommended and post on CCLE. So you can check the details if you're interested. Okay, so this is just the logic behind the first important result about MLE, the consistency. The second result is that we want to know the distribution, the asymptotic distribution of the MLE in relation to the true parameter, right? So knowing that there's a convergence is not enough for us to describe the randomness of this, MLE, just as we have seen for the sample average, sample mean. We show that sample mean converges in almost surely or in probability to the population mean by the strong law of large numbers. And then we have the central limit theorem for the asymptotic distribution of the sample mean, right? So the strong law of large number is one thing, and the central limit theorem is the second thing. So here we're going to have another central limit theorem version for this MLE. So we'll see how that will work. Okay, so for that part, the Taylor expansion or mean value theorem will be our tool again. Okay, so first of all, let's come back to this average here, which is the log likelihood divided by n. Okay, so with that, how do we do the expansion? So first of all, we will work with this law. So we'll work with this log likelihood and its derivatives. So second topic, asymptotic distribution. Okay. So basically, we're going to work with this root n times theta n hat minus theta 0. We're going to derive what distribution it converges to. Okay, so in order to do that, let's first take a look at an important property about the MLE. That is, if the log likelihood function is twice differentiable, just put it this way. So if I'll say this ln is twice differentiable and has a continuous second derivative in the neighborhood of the true theta 0. So with this condition, we would like to apply Taylor extension. Okay, and for the theta n hat, the MLE, what we know is that in this case, right, for such a log likelihood, we can have the MLE to satisfy that it is a solution of the first derivative equal to 0. Setting the first derivative equal to 0 gives us a solution. And maybe one, if it has multiple solutions, then one of the solutions would be the MLE. So for those nice condition, log likelihood. Okay, so we can say that the first derivative of the log likelihood evaluated at MLE is equal to 0. So this gave us a very nice way to expand the first derivative of likelihood at a true parameter value or based on this result about the MLE. So what we would have is this. So based on the mean value theorem, what we have is the first order log likelihood evaluated at theta n hat, okay, can be written as this function evaluated at the true parameter theta 0 plus, okay, the derivative of that, the second derivative evaluated as somewhere between these two things. So I'm just going to call that as probably theta n hat prime, I'll just call that, times the theta n hat minus theta 0. Okay, so where this theta n hat prime lies between those two things. I'll just say, yeah, so maybe if I just, it's okay which side is bigger than that, but I'm just writing it as theta n hat, theta 0, or other way around, but it's just in the middle of those two. So with this, you see, what I want to do is that I want to create this form, theta n hat minus theta 0, and I have it here. And what I also have is that the left-hand side is equal to 0. So that gives me some convenience. So with this result, I could actually obtain that theta n hat minus theta 0 would be equal to negative this first derivative at theta 0 divided by the second derivative at this theta n hat prime. Okay, so I have that. So now my question for you is, why is where? So obviously on the left hand side we have the MLE as a random variable, and on the right hand side, where is the randomness? Can somebody answer this question for me? So obviously theta 0 is not random, right? And here in the denominator, this theta n hat prime must be random because the one of its boundary is random. But what else? Do we still have some additional randomness on the right-hand side? So it's actually, I can give the answer. It's actually this ln, because this log likelihood is defined based on a random sample, right? It's the sum. So coming back here, this ln is defined in this way. It involves x1 to xn, and that's a random sample. So that's why this log likelihood function is random. Okay, so because it's a random function, then its first derivative, second derivative are both random. Okay, so what else can I say about that? So the first thing we can actually say is regarding the right-hand side. So let's think about what distribution it has. Okay, so this for the right-hand side, the question is, how does it converge in law to somewhere? Okay, so we don't know whether we need divergent constant like root n or n yet, but we are considering that option. So for now, in order to derive the asymptotic distribution for this term, we need to use Slutsky theorem. So the hope is that for the numerator, we are able to derive its asymptotic distribution. And for the denominator, we are going to find a limit in a constant limit in probability. So if you recall that, if we combine those two things, one is a random variable sequence converging to a distribution. The other is a random sequence that converge in probability to a constant. Then putting together, we can have an asymptotic distribution. So that's the direction we would go. Okay, so let's first take a look at the numerator. Okay, so the numerator, if we look at it, we can actually see that, okay, this thing. So actually, in statistics, the derivative, first derivative of a log likelihood, we actually give a name, and it's a jargon called score function. So this is the score function. And look at it, right? So it's just this log likelihood, right? Doing a differentiation against theta. So by the chain rule, we are able to show that, no, this is d theta right? And by the chain rule, we are able to show that we are going to have f theta xi as the derivative log. Then we have this, right, f theta prime xi. So we are going to have it as this. So this score function has very nice results or properties. The let me see, I missed something. Okay, theta 0. Yeah, I need to evaluate theta 0, theta 0, theta 0 here. Right. The first nice property is that I can show the expectation of this Ln prime theta 0 evaluating at theta 0, which is a true parameter for the xi's. I can obtain 0. It has 0 expectation. And we can show it based on the definition of expectation. So that is, imagine that you're doing integration here. Then you are going to have an f theta 0x multiply here that can be canceled with this in the integration. And then for this differentiation, I'm just going to change the integration outside and the differentiation inside. So this can be allowed as long as my density function satisfies some regularity condition. So with that, I can put the differentiation outside, and the integration of this term alone will give me 1, value of 1. So then value of 1's differentiation will be 0. So this is just how we can show that this thing has mean 0. Okay, that's the first. Okay, and the second thing is that now you see this thing itself is some average as well, right? It's just if I divide this by n, it's an average of IIDs evaluated in this way. So therefore, you can see that by the central limit theorem, which I can apply, root n times 1 over n times this term, okay, minus its mean, which is 0, would converge in law to a normal distribution with mean 0. And the variance is what? The variance of this term. The variance of f theta 0 prime xi, f theta 0 xi. Okay. That's it. So I have this bicentral limit theorem, which is very close to what I would need over here, okay? Because I have something about this. So what's left here is how can we calculate this variance, right? So for this one, actually, I can tell you that this variance, it can be basically calculated as the inverse of what we call the Fisher information. So if you have heard of that term, then basically the Fisher information is defined as I need to make up this. So the Fisher information, we can write it as a function of the parameter, a parameter value we want to evaluate. Okay, so what is that? We often use this I for information. Okay, so what we can show that it can be defined as, assume that I just have a sample of size 1, okay? So not considering all the sample sizes, when n is equal to 1, then I have just only one random variable from the distribution. Then the Fisher information can be shown as the, let me see. It can be shown as the expectation of the square of the part of the derivative. Okay, theta x. Okay, so it's the log density at this value theta of the random variable x. I take the differentiation and I square that. And we can also show that by the special property about this thing, and also the expectation is valued at this theta. We can also show that this is equal to the negative expectation of the second order differentiation, d theta squared log f theta x. Okay, so either way, this is how we can define the Fisher information. And if we have a sample of size n, then we can show that the Fisher information for the sample would be n times the Fisher information with just one random variable. And that's a result. So over here, so coming back to what we have over here. So essentially, you see why I'm saying we are close to the Fisher information is because, so given the definition here, you can see that the I theta with sample size 1, if I do the differentiation, I just expand this term, I would have f theta x here and f prime, the derivative of the density x. I would have that. Okay, and also I know this term has expectation 0. I know the e theta of f theta prime x, as I just said, f theta x. This has 0 expectation. So therefore, when the expectation is 0, then the expectation of the square would be equal to the variance. Right? So that's why I'm saying that essentially what I have here is the Fisher information. Okay, so Fisher information at the true parameter value. That's it. And this is about the denominator, sorry, the numerator in this term. So how about the second derivative of the likelihood function? Now let's go further. So for the L and double prime theta 0, so looking at it here, so I'm just going to do the differentiation again. Okay, and no matter how I do it, you see, it's still some sum of IID, right? So it's still so all the differentiation would happen inside the summation. So that means I can say that this thing, if I divide it by n, okay, would converge in probability to the expectation of this d theta xi theta 0. That's what I would have. So again, I'm taking differentiation on the left-hand side as well as the right-hand side because it's a finite sum from 1 to n. The differentiation goes in here. So that's why I'm doing this, right? And then if you look at here, it's what? It's basically this, right? So you see, I'm doing this as this is like the second derivative, right? So what I'm saying is, if you look at the form, d theta, inside it, it's basically f theta, sorry, it's basically d theta log f theta 0 at xi. right? So I use this first. I use this first to go to by the chain rule to obtain this form. Now I'm going back. So essentially, you see, this is just like expectation of d theta squared, the second derivative of log f theta 0 xi. Okay, and what do I have here? This is just the negative Fisher information at theta 0. Okay, so putting it together, you see what I'm having here is, so coming to here. So theta n hat minus theta 0 is negative. Okay, I can put 1 over n here. ln prime theta 0, the first derivative divided by 1 over n ln double prime, second derivative. Okay, and for the numerator based on what I have here, you see, I know if I multiply by root n, which I can do on the left-hand side here, root n, okay, minus 0, it doesn't change anything. I can know the numerator is going to converge, you see, to this normal distribution with Fisher information as the asymptotic variance. While the denominator right here is going to, I can put a negative sign to the denominator. It's actually, if I put a negative sign here, it's convergent to the Fisher information in probability. And it's in the denominator. So basically, you see, I can write it as negative 1. So 1 over negative 1 over n, this, okay, times what I have with asymptotic distribution, 1 over n. Okay, I can write it this way. So what I just said is that this term, I know from this, right? And also the continuous mapping theorem, which is basically the first statement of Slutsky if we apply the convergence in probability version. This is converging in probability to 1 over the limit, right? And 1 over the limit is this, 1 over to that. And this term is converging in law to normal distribution with mean 0, variance Fisher information. So putting together by Slutsky, we would have, this is a constant coefficient, which will enter as a square into the variance term, right? By Slutsky, we would have our final result. Conversion in law to normal distribution. This will be squared into here and cancel this one, 1 over Fisher information. That's it. So you see, this is how we derive the asymptotic distribution of the MLE. Still, we utilize Taylor expansion as the basis for doing this. And we use multiple properties about the log likelihood function, including that if you take the first derivative of the log likelihood function and you take its expectation, you get 0. That's the basis for doing this Taylor expansion here. And because of this step, we can explain this difference in terms of the first derivative and the second derivative of the likelihood function. Okay, and one thing I ignore, actually, I didn't make it clear. You see, here I should have second derivative of log likelihood function evaluated as somewhere between the MLE and the true parameter. But when I wrote it here, I used the true parameter. I ignored that theta n hat prime. The reason is because by our first result, we know the theta n hat would converge, right, strongly in probability to theta n, to theta 0. So that's why we know as n goes to infinity, this term would become ln double prime theta 0. So that's why I'm just using this ln double prime theta 0 to derive the final result. So we skip several details here, but I hope that you get the basic essence about why we have this result. Right? So I'm saying that essentially, although I'm talking about here, but I should be working with this. Okay, I should be working with this. And I know that we know that this thing, which is random, will converge in probability to theta 0 from our consistency result. Okay, so do we have questions about how the asymptotic distribution of the MLE was derived? And I think so basically I was assuming that people have some basic knowledge about, say, the score function and the Fisher information. So that's why for those things, I didn't prove. I just directly used the result. But if this is something new to you, I think it will be good to know as a foundation of our statistics, especially for parametric inference. Okay, so any questions before we try to show an example and wrap up today's special lecture? Okay, so let's show a simple example. Okay, so let's see that we have example. Okay, let's say that we have x1 to xn IID from a Bernoulli distribution, the simplest distribution with parameter theta 0 using our notation, right? This theta 0 is between 0 and 1. Let's say that. Okay, so the first thing we want to say is how does the MLE behave, right? We actually know, if you know MLE really well, you would know that theta n hat would be just the average, right? So in this case, we know we can directly use the central limit theorem, right? So we would know that by CLT, root n theta n hat minus theta 0 would converge in law to 0, and the variance would be the variance of xi, right? We know for Bernoulli, variance of xi is theta 0 times 1 minus theta 0. That would be the asymptotic variance. But let's see, we don't know this, okay? If we don't know this, we assume we just use the general MLE theory we just derived. Then what would that look like? To do that, we need the Fisher information. Okay, so for Fisher information, I found it easier to use this formula. You just take second derivative of the log density function, then you take the expectation. Okay, so let's look at the f theta 0 x. Okay, what's that? For any x or xi, it doesn't matter. It's just a notation. So we know the density function, or here we should say probability mass function to be more exact, of a Bernoulli is just theta 0 to the power xi times 1 minus theta 0 to the power 1 minus xi, right? So whenever xi takes value 1, the probability is theta 0. Otherwise, it's 1 minus theta 0. So taking the log, we would have xi times log theta 0 plus 1 minus xi times log 1 minus theta 0. Okay, then we take derivatives against theta. So d theta f theta 0 xi, right? So we still evaluate this derivative at theta 0. So we keep theta 0 with us. It's just theta 0 xi minus 1 minus theta 0 because of negative sign, 1 minus xi. That's the first derivative. Then how about the second derivative? Let's just go one more. This f theta 0 xi, I'll just directly write the result. It's actually negative theta 0 square xi minus 1 minus theta 0 square 1 minus xi. Okay, finally, Fisher information, which is the expectation of that. I'll also evaluate at theta 0. Okay, putting this inside, I'll just write the result directly. Negative theta 0 squared, expectation of xi, theta 0, minus 1 minus theta 0 squared, expectation of that, 1 minus theta 0. So we can quickly see that, oh, sorry, I forgot the negative sign. Yeah, this is the negative of the second derivative. So negative and that, so I cancel the negative sign in both terms. And also after cancellation, I get 1 over theta 0 plus 1 over 1 minus theta 0. So I get this. Okay, we're done. So given this result by the MLE asymptotics, right? The one we just derived, we have root n times the MLE minus true parameter converging in law to the normal distribution and the inverse of the Fisher information. So that is theta 0 times 1 minus theta 0. So we obtain the exact same result as we got from the CLT, central limit theorem. So this is just one application example to show how we use this in practice. So in practice, if your parameter is multidimensional, okay, so let's say if theta 0 is RP, then you need a multi-dimensional version of what we did. So which can be a little bit trickier. We need to deal with matrices and vectors, but still the result is the same. So you have the p-dimensional asymptotic distribution, right? This will be a Gaussian p dimensions, right? It's a p-dimensional Gaussian zero mean vector, and then it will be the Fisher information, which will become a p by p matrix. And also the Fisher information matrix is always positive definite. So you can take inverse as the covariance matrix for the asymptotic covariance matrix. So that's it. And what else do I want to say? Maybe I can say something about the interpretation of Fisher information. Why does it make sense? I think looking at it this way will help us evaluate it. So look at it. So think about this way of writing the Fisher information. So it's about what? The numerator is the derivative of the density function, and the derivative is regarding changes in theta. So it suggests that if you take theta to be left or right of its value, then how, or if it's true value, let's say, then how fast does the density function changes, right? So, and here we take the square, so we don't care about the sign of the derivative. So essentially, it's evaluating that given my data or given the random variable from my set distribution, then at this particular theta value, if it is the true theta value, if it is true parameter, then if I alter my parameter value from the true value, how much do I change in the density function value? So you can imagine that if it changes a lot, it means that given your data, you have better ability to distinguish the value you currently have and the true value, right? Because that the true value is really distinctive. If you go away from it, you expect a big change in the density. Then that indicates, yeah, the estimation problem for this true parameter is easy, because we know that the density will look very different at another value compared to the density at a true value. That's the intuition behind it. So that's why Fisher information being large is a good thing. It means that given this parameter, this parametric distribution you specify, and if this is the true value, then you have very good ability to detect this true value. And this intuition is also reflected here. You see, having a large, I should say theta 0. and also 0, my bad. Yeah, having a large Fisher information at the true value, it will give you a small asymptotic variance. That means your MLE will be closer to the true value, and the MLE will have smaller uncertainty given the sample size. So I hope that you will find those things now have some connections. So, right, so I think this topic, and I didn't actually talk about it before, and it's not part of our homework, but I think it's something good to know. Yeah, I'm not sure if everybody here have learned this in some way before, but if you did, maybe you can raise your hands and let me know. Okay, so let me see. I don't see any hands. So, so any questions before we wrap up this part? Yeah, I think for everything I talked today, we can go into lengthy details. So that's why if you read some advanced textbooks, you can see the details are very overwhelming. But I try to give you the big picture, the main ideas here to walk you through how we achieve this. But I think for my other class, which I taught in past years, not this year, the linear model class for grad student, it's the course number is 205. So in that class, we did use a lot about these properties about the log likelihood for deriving the algorithm, the optimization algorithm for finding the MLE for generalized linear model. So in that case, because the likelihood function is not easily differentiable. So you cannot just say, okay, I find the first derivative, I set it to 0 to find a closed form solution for the MLE. So in that case, we need some iterative algorithm to find a solution. But in that case, and we use Newton-Raphson. So in that case, we have to talk about the first derivative and the second derivative of the log likelihood function, because that's the function we want to maximize. And we use some nice properties about the fact that, yeah, the first derivative has expectation 0. So in that case, knowing this, you may replace the first derivative by its expectation, just to simplify the optimization problem itself. Okay, so I think that's it. That's about the MLE special lecture I want to talk today. And so next lecture, we will come back to our extreme order statistics. So I may show one more example, and then we will talk about the sample quantiles. So which are related, but not exactly the same. Because when we talk about sample quantiles, we are often interested in the non-extreme orders, like the median, which is in the middle, right? But for the past lecture, we were talking about the maximum, second largest maximum, and the minimum. So for those extreme orders. So that's primarily the difference. Okay, so before I end today's lecture, do we have questions from the audience? So maybe just because we have 10 minutes to go, I just want to say that although the proof, right, for this MLE theory may seem a little bit tedious or complicated, but to apply the theory is actually very easy. So everything you need to do is the Fisher information, whether a matrix or a scalar. You just need to find the density function, our joint density function, right? No, or actually, I shouldn't say that. You just need to find the density function of your distribution. So what I want to say is that if the parameter distribution has more than one parameters. So for example, x1 to xm, if it's IID from normal distribution. Okay, so if that's the case, then the Fisher information will be a 2x2 matrix. Okay, so in this case, when you talk about the Fisher information, it would be for mu and sigma squared jointly. And then what you would do is that you are going to take the expectation of the negative. This is what we call the Hessian matrix. Okay, so basically you're going to do like this is partial mu square, and you will have the normal density, which I'll just write this, phi mu sigma square. Okay, that's the thing you will have. And right here, you will have partial, right, sigma square. You take differentiation for twice of this normal density and mu sigma square. And here in the off diagonal, you're going to have partial mu, partial sigma square, mu sigma square. And also here by symmetry, it's actually the same. So the same thing here. So you are going to derive this Hessian matrix by taking the normal density and its partial derivatives against mu and against sigma square. And then as we know that it will involve x, right? So x will be what you take expectation for. So it's expectation for random variable xi that follows this. So that's why the term xi. And that's how you calculate the facial information. So I think probably one thing that's not very obvious for beginners was the question I asked in the middle of this lecture. That is, what is the randomness in the likelihood function, right? So because it's a function. So when we say likelihood function, we may not realize that it's actually random, but it is. If we consider our sample to be random, then the likelihood function based on the sample would be random. So I'm going to post the notes is already on CCLE, so you can check that to walk through the details. And I can post another notes which contains more technicality about what we just said. Okay, so if there are no more questions from you guys, so we will end today's lecture here, and I'll see you in class in the Friends Hall, that classroom next Monday. So we will come back to the extreme order statistics. Okay, bye everyone. Bye.
Bye.
Bye.